Now you're tricky.
It is exactly noon, 12,
Oh, 12.
2.5 hours.
Okay, Professor. Okay.
Exactly 2.5 hours between Turkish time and Indian Standard Time.
Okay, Professor. Join பண்ணுங்க. start பண்ண போறாரு.
Good afternoon, all. Life is a math equation. In order to gain the most, you have to know how to convert negatives into positive. Let's begin the session with a warm welcome to our respected principal, Dr. R. Ruben, Administrator, Reverend Sister A. Malachoti, Resource Person, Dr. Ismail Naci CANGUL, Vice Chancellor, DMI, Eugene University, Dr. R. Kavita, faculty fraternities, and all the participants for this FDP. St.Joseph College, Arts and Science is a co-educational Christian institution run by the Management of Society for Education for Life. This college has been established in 1994 and has been taken over by Reverend Father Dr. J.E. Arulraj, DMI, and managed by Sisters of DMI from 2004. In our college, we are offering 13 UG courses and 4 PG courses. The Maths department is the major department in the college, which has been started in the year 2006 with 7 students and 3 faculties. Now it is strengthened with 70 students and 14 faculty members. Once again, I wholeheartedly invite you for the 6 days faculty development program on recent research advanced in mathematics. Now I would like to call upon Mrs. D. Flora Evangeline, Assistant Professor, Department of Mathematics, to start the session with blessings of prayer.
Thank you, ma'am. In the name of the Father, and of the Son, and of the Holy Spirit, amen. God, our loving Father, we praise you and thank you for bringing us together to a new day. As we begin our day, we offer ourselves to you through this faculty development program, and forgive us all our sins and bless each and every one of us connected here. We offer ourselves before you and seek your grace, enlightening our minds and open our hearts so that we may enrich our knowledge, discipline, and use them for nurturing your minds. We offer this prayer in the name of Jesus Christ our Lord. Amen.
Thank you, ma'am. Thank you for your blessings. Now, may I request Mr. K. Sujata, Head, Department of Mathematics, to give the welcome speech.
A very good afternoon, everyone present here. Myself, Mrs. K. Sujata, Head, Department of Mathematics. I extend a warm and hearty welcome to each one of you for the 6 days International FDP on recent research advances in mathematics. This program is organized by Department of Mathematics, St. Joseph's College, Chennai, in collaboration with DMI St. Eugene University, Zambia. The main motive behind this program is to create the awareness on latest thrust areas in mathematics among the faculty members. With the blessings of God, the Almighty, and Founder Father, Reverend Father Dr. J.E. Arulraj, I would like to welcome our respected keynote speaker, Dr. R. Kavita, Vice Chancellor, DMI St. Eugene University, Zambia. I extend my warm welcome to our administrator, Reverend Sister A. Malachoti, and our eminent principal, Dr. R. Ruben, for the guidance and support in conducting this faculty development program. A special mention to Dr. Ignatius Herman, Director of Education, DMI Group of Educational Institution, Central Africa. We feel gratitude in welcoming our resource person, Dr. Ismail Naci CANGUL, Professor, Department of Mathematics, Uludag University, Turkey, for today's session on graphs and its application. I extend my welcome to Mr. Govindan, Research Coordinator, DMI, St. Eugene University, Zambia, who coordinated the resource person for today's session. Thank you very much for your support, sir. Also, I welcome our dignified faculty members of our department, our college, and other colleges and universities across the country. I hope you will enjoy the program. It will be great and successful. Once again, I welcome you all to day one of the International Faculty Development Program on graphs and its applications. Thank you all.
Thank you, ma'am. Now, I humbly request Dr. R. Kavita, Vice Chancellor, DMI, St. Eugene University, Zambia, to give the keynote address.
Thank you, madam. Good afternoon to all. I feel very much honored and privileged to address the learned members of the society. I thank the organizers of DMA St. Eugene University, Zambia, and St.Joseph College of Arts and Science, Kovu, Chennai, India, for the effort taken in this endeavor. DMA St. Eugene University is located in Zambia, in Southern Africa. Zambia is rich in natural resources, especially in copper, gold, silver, zinc, uranium, precious stones, etc. Zambia is the land of legendary walking safari, Victoria Falls, wild Zambezi River, abundant wildlife, and raw wilderness, all in one friendly country. Zambia is very happy to collaborate with India on this occasion. I would like to appreciate and thank the team for conducting the 6 days faculty development program on recent research advances in mathematics. Mathematics is the gate and key to the science, and Archimedes is the father of mathematics. Mathematics teaches us multiple problem-solving ability like equation, computation, or algorithm, which help us advance in multiple aspects of life. The most famous saying in mathematics must be, everything around is number and everything around is mathematics. So, all scientific education which does not commence with mathematics is said to be defective at its foundation. Neglect of mathematics works injury to all knowledge. Mathematics has played a very important role in building up modern civilization by perfecting all sciences. The purpose of this FTB is aimed to promoting academic and research excellence in institutions with peers. It provides platform for faculty and enthusiast researchers to interact with experts in their specific field and discuss new challenges and trends in the area of mathematics. Mathematics is a creation of human mind, concerned mostly with ideas, processes, and reasoning. It is much more than arithmetic, more than algebra, more than geometry. Also, it is much more in trigonometry, statistics, and calculus. Mathematics includes all of them. Primarily, mathematics is a way of thinking, a way of organizing a logical proof. Creating, spending budgets, paying for grocery, buying things on sale, and cooking meals all have to deal with mathematics in some way or another. One has to be able to measure out ingredients, count money, and determine limits when it comes to certain tasks like examples above. People never realize how much mathematics is around them until they take a step back and look. Music production requires a solid knowledge of mathematics. Music's tempo, pitch, and volume are actually mathematical functions. Tempo is a proportion, pitch is a property of a sound wave, and volume is measured in decibels, which are in a logarithmic scale. Electronic dance music, a new type of music, is totally produced on computers. Beats per minute is a basic trait that mixing and producing electronic dance music requires. Especially today, music make thus means knowing mathematics. Moving on, statistics play a pivotal role in our daily life. These numerical data are used in influencing the decisions we make. When playing games, we tend to choose characters with higher statistics in order to give us an edge in winning. Statistics is also commonly used when it comes to exams and companies' annual reports. Even students and workers alike hail the bell curve as it shows how well one has performed. Based on the standards of cohort, the bell curve has helped numerous students attain their desired grades and work to meet their quotas, thus earning their well-deserved bonuses. Discrete mathematics examines objects that can be represented finitely. It includes a variety of topics that can be used to answer various tangible inquiries. It involves several concepts including logic, number theory, counting, probability, graph theory, and recurrences. Discrete mathematics provides an important foundation for all areas of computer science. Discrete mathematics is used in various areas including computer architecture, algorithms, computer systems, databases, functional programming, distributed systems, machine learning, operating systems, computer security, and networks. The problem-solving methods taught in discrete mathematics are needed for composing complicated software. Machine learning and artificial intelligence, especially in hidden Markov models, mathematics shows in a spectacular way how some part of our brain might work to predict certain outcomes of a system. You can actually see how the algorithm is thinking and predicting things with equal, but usually better, efficacy than you. Google Translate, Google, now and pretty much every software that you talk produces something, while uses hidden Markov models for that. Word suggestions in Google search bar use hidden Markov models. The face detection software, camera, smile detection, etc. are one or several hidden Markov models used. Robots, trying to make sense of the world by looking or hearing also use hidden Markov models. But what the heck is a Markov model? The word model here stands for a couple of matrices and one vector. That's it. It allows you to predict and pretty faithful in some cases, things, observes, and almost anything. With so much application of mathematics involved in our daily lives, I hope that you are able to see the beautiful side of mathematics. In reality, the magic in mathematics can be seen through probability, statistics, and also art forms around us. Sometimes we just have to take a step back and appreciate how mathematics has benefited us in our daily lives. I would like to once again quote from the famous mathematician Arthur Benjamin. Mathematics is not just solving for X, it is also figuring out Y. Mathematics and pedagogy are more important for all education systems. If and when mathematics is removed, the backbone of our material civilization would collapse. It is now important for the researchers to develop and create interest in mathematics to our 21st century generation who are recently avoiding mathematics. Finally, I wish all the members and callers for your valuable contribution for the success of the FTB. I congratulate the Indo-Zambia collaboration. God bless you all. Thank you for the opportunity.
Thank you, madam. Thank you for your valuable speech. Now, I would like to call upon Mrs. De Flora Evangel,
Thank you,
Assistant
ma'am.
Professor, Department of Mathematics, to introduce a resource person of today's session.
Thank you, ma'am. It's my immense pleasure to give a brief introduction about today's speaker, Dr. Ismail Naci, CANGUL, Professor, Department of Mathematics, Uludag University, Turkey. He has been working as a professor in the Department of Mathematics, Uludag University. In 2013, he became a member of the interdisciplinary MSc program called Criminalistics under the Institute of Science at Uludag University. He attended over 100 meetings and gave many seminars. He was the supervisor in 3 European Union student projects, and he also took part in 3 European Union student projects and 17 scientific research projects from QBTAC. He had been a reviewer of 2 European Union projects on quality culture and institutional review. He had been the Dean of Faculty of Arts and Science for 6.5 years. He had written 49 books, 200 scientific research papers. 20 of his scientific papers have been awarded QBTAC Scientific Paper Support Program. He has the highest number of academic activities among all the academicians at Uludag University. He had been awarded several awards and rewards. Some of them are the Scientist of the Year Prize in 2012, Annual Successful Academic Prize in 2012, the highest number of annual publication prize in 2013, and the Best Performance Award in 2016, etc. He is also a member of 6 national and international mathematical societies. I wholeheartedly welcome our resource person, Dr. Ismail Naci, CANGUL, Professor, Department of Mathematics, Uludag University, Turkey. Thank you, sir.
Thank you, ma'am. Okay, hello everyone. I'm very excited to be a part of another nicely organized meeting. 6 days International Faculty Program Development Program in St.Joseph College in Chennai. One of the beautiful places, most beautiful places in India. And also this is organized in collaboration with DMI St. Eugene University in Zambia. I haven't been to Zambia yet. Hopefully one day, if my life is long enough, I may have the chance to visit. I like going places and meeting mathematicians always. So I especially like to thank to my friend and co-author Govindan Vidyapan for his invitation, for his kind invitation, and all faculty members in both universities. Today, I will be talking about graph theory and the topological invariant in graph theory. So maybe I should start with, yes, I think it's on. The title is Omega Invariant and New Applications. What is Omega Invariant? I will be talking about this because it's a new invariant. You know, invariants are always important in several areas of mathematics. In every branch of mathematics, there are invariants which are very important to classification, to you know, making catalogs of things. Here, omega invariant that was defined 3 years ago approximately will be introduced, and some applications of it will be given. At the beginning, after some motivation, I shall give you some problems. And these are hard problems in graph theory, normally unanswered open problems. By omega invariant, you can answer most of them. So I will be giving examples of these problems. First, I will list the problems. Then after some introduction, I shall answer the problems. At the end, I will give some recent applications of omega invariants. So let's start. First, some fundamental things. Of course, not everybody in the speakers are familiar with graph theory, so I will be trying to give everything in details, brief details at least. A graph is a picture. You all draw many pictures as a graph, probably, without intending it. Because it is consisting of some dots, some vertices connected by some lines. So everywhere around you there are graphs actually. More importantly actually, graphs are useful in many areas of science, in chemistry, in communication, in medicine. Of course, there is no time to talk about all the applications of graphs, but from time to time during my talk, I shall try to give you examples of this as well. But most of the talk today will be on the fundamental notions of graph theory. The thing is actually, maybe I should tell, we can model real life problems by graphs. If there are persons interacting in some way, communicating with each other, being in the same group, social group, or talking the same language, this kind of connections, this kind of groups can be modeled by graphs, okay? Because people can be represented by dots, vertices, and the relations between them can be drawn by some lines called edges in graph theoretical terms. So, or a chemical molecule, for example, ethane, methane, anything, hexane, you can put a vertex for each atom, carbon, oxygen, and dot. And if they are connected by a chemical bond, then you can put some line between these atoms, between these vertices, okay? So you can study chemical molecules without going to a laboratory, without spending any money, okay? So it's a good way. It's a clear, clever way of studying chemistry by mathematics. This is graphs, okay? Since 1947, when Harold Wiener discovered some new formula for melting points, boiling points actually, boiling points of some alkane classes, it started a big study actually. So you can search for Wiener index, for example, in that terms. All right, let's continue. A graph is called connected. Connectedness is an important topic, you know, in mathematics in many branches. Here in graph theory, a graph is called connected if there is a path between every pair, every selected pair of vertices. That means from one vertex, you can go to all other vertices without leaving the line, okay? A graph, of course, that is not connected is called disconnected. Given vertex degrees, we call degree sequence, I shall introduce in a few minutes. It's an open problem that the realizations of these vertices as a graph would be connected or disconnected. This is an open problem. In this paper, maybe most important applications of omega invariant is to determine the connectedness of realizations of a degree sequence. I shall give you in a minute. So, ds denotes degree sequence of a graph. It is a non-decreasing, usually non-decreasing, sometimes non-increasing. It depends on your aim. Sometimes you have to organize these numbers in increasing number sequence, or sometimes non-increasing. Both possible. Here we take non-decreasing sequence of non-negative integers, which are the degrees of the vertices. I shall give you concrete examples. This is written with multiplicities. This is a degree sequence. Okay, this means there are vertex degrees D1, D2, D3, and delta. Delta, capital delta, is the biggest vertex degree. Okay, with multiplicities A1, A2, A3, and A delta. Okay. In a minute, I shall give you more concrete example. But before, I should give you some more definitions. This is a set of non-decreasing set of non-negative integers. There are zeros or positive integers here, okay? The biggest one is capital delta. We say that a graph G is a realization of the set of this set D if the degree sequence of G is equal to D. That means you are given a set, okay? A set of non-negative integers. Usually we exclude zeros as well because zero means degree is zero. So this is isolated vertices. Isolated vertices are not very useful, okay? Just several vertices around. So usually we have positive numbers starting by 1, 2, whatever, okay? Going up to 55, 10, whatever, okay? So this is a set. Then we say that a graph is a realization of this set if the vertices, vertex degrees of this graph are these numbers, these integers, okay? So this is a concrete example for those who are a little bit away from graph theory. For example, this is these two graphs. You see, these are first two graphs you see in this talk. They have one vertex of degree 1 because it connects to one another vertex, okay? This is of degree 1 because it connects to just one vertex of degree 3. This vertex here is of degree 3 because it is connected to 3 other vertices, okay? And finally, for example, this one is of degree 2 because it is connected to this one and this one, okay? These are vertex degrees. If you order them in a non-decreasing order, then you get a set like 1 to the 1 because both have 1 ones. Triple twos, 1, 2, 3. Here again, 1, 2, 3. And ones 3, vertex degree 3. Here the 3, and here it is the vertex degree 3. Okay? So that means these two graphs, this one has triangle, this one is a quadruple, for example, then they have the same degree sequence. This gives you another problem, dear friends. For example, given a set like this, 1 to the 1, 2 to the 3, 3 to the 1, how many realizations are there? We don't know this. We don't know. It's an open problem. If you can find a formula for this, or even we don't know the number of graphs, a given number of vertices. Of course, it is known forcible vertex numbers, for example, up to 5, 6, 10. You can find them in the internet easily. But for example, how many graphs are there with 50 vertices? I don't think it's known. It's a very, very, very big number. You cannot read it probably, okay? So these two graphs have the same degree sequence and they are realizable. This degree sequence here, 1 to the 1, 2 to the 3, 3 to the 1, we call this realizable degree sequence. Of course, given such a set of positive integers, we wonder about its realizability. Of course, before us, many people wondered about this, and there are some criteria like Havel Hakimi since 1950s, 60s, and the others, Erdős, Gallai, Reiser, Berch, Fulkerson, Hoffman, McAndrew, Balobas, Grunbaum, Hasselbart, Siegsma, and Hugoven criteria. These are all criteria, algorithms. You start with the degree sequence you are given, and you do some algorithm, you apply some algorithm. After some steps, you get something you know. For example, in Haval-Hakimi process, you start with the largest vertex degree, you order them, then you apply some algorithm until you get some smaller set, which you know that realizable or not, okay? So the realizability of the set you started with is the same with the ending set. So you can decide about realizability after applying these algorithms. Of course, the obvious, we all know about, all graph theorists know actually, about the handshaking lemma. So it says that the sum of vertex degrees must be even. This is an easy criteria because it is equal to twice the number of edges, the size of graph. So if it is equal to twice the number of something, then it must be even. So the sum of vertex degrees must be even. For example, here, 1 to 1, 1 times 1, 1. 3 times 2 is 6. We have 7 already. And 1 times 3 is 3. So altogether we got 10. 10 is even. If it was 11, then we could not have such realizations, okay? It must be even. The sum of these numbers with multiplicities, okay, must be even always. So this is another criteria for realizability. Now, I shall, as I promised at the beginning, I shall give you about 7-8 problems. The solutions, you can think about it. If you are a graph theorist and if you don't use omega invariant, if you are not aware of it, then you cannot solve these problems, any of these problems, easily or completely. So omega invariant will help us to solve all these problems. Before I finish, I will give you the answers of these problems. The first problem is, given a degree sequence, a little bit more complicated one than the before, is it realizable? And the second question here in this page, what is the cyclomatic number? Cyclomatic number is related, closely related to omega invariant. It is the number of independent cycles I shall talk about. The second problem, it asks us to find two realizations with minimum number of components for this degree sequence or maximum number of components. Given this degree sequence, okay, there are 4, 6, 8 vertices, okay, 8 vertices. 2 of them are of degree 5. 2 vertices are connected to 5 neighbors, okay. 2 of them are of degree 4, and there are 4 vertices. Each are connected to 3 other vertices, okay? So, now, how many realizations are there? We don't know, okay? Still we don't know. With omega invariant, still we don't know. It's an open problem. It is very strong, very hard problem, okay? But it asks us with minimum and maximum number of components. That means, for example, are there any connected realizations? If there are connected realizations, the minimum number of components will be 1 because it's connected, just one piece, okay? But what is the maximum number of components with these degrees? We shall give a theorem for that, okay? Just try to remember the problems a little bit because I will give the same problems later with answers, okay? The third problem is to find the number of distinct cycles. You can start counting, for example, E, Phi, and B, E, F, and B. It's a triangle. There is another triangle, E, A, C, for example. There's a quadruple E, C, H, B, for example. But they are overlapping each other. So it is difficult to count. It's about maybe 10, I don't know. It's difficult. You remember, you should remember which one you counted. And as they overlap, it is really difficult to keep track of it. Another problem is about finding the number of chords. What is a chord? In a graph, let me show. This is a graph, and there is a big cycle around it. It's an octagon. There are 3, 4, 5, 6, 7, 8 vertices around it, okay? So the line from F to G, this edge, FG, is a chord. The definition is it's an edge connecting two non-adjacent vertices. Non-adjacent, okay? They should be non-neighbors, non-adjacent, okay? If there is an edge connecting two vertices which are not neighbor on a cycle, then this is a chord of the graph, okay? How many chords are there? Which cycle you should take? We should consider. There is another problem now. Okay. There is another problem. D is equal to 1 to the 11, so you can read it. Then how can we find its connected realizations? You know, we don't know about how many realizations are there. We don't know, are they connected or not? So it asks us, how can we find its connected realizations? Maybe there is none of this type, okay? We don't know yet. Another problem, how can we decide whether a realization of a given degree sequence is connected? Another similar question. And to repeat all the findings, all the results, I gave a complete problem, not complete, lots of problems for the same realizable degree sequence. Is this degree sequence realizable? Are the realizations connected or disconnected? What is the minimum maximum number of components? For example, can you give a realizations having 3 components, 3 pieces, 1, 2, 3, disconnected 3 components, okay? Are the realizations cyclic? Are the realizations cyclic or acyclic? Cyclic means there is a cycle, closed circle, okay, with some vertices on it, okay? Acyclic means trees. We call them trees, or of course forests if disconnected, okay? I shall be giving examples. What is the minimum or maximum cycle length? The cycle length, for example, how large it could be or how small it could be. We can determine all these. We don't know every realization. We don't know the number, but we can decide about many extremal problems, my friends. For example, maximum and minimum cycle lengths, maximum and minimum number of loops. Loop means an edge starting and ending at the same vertex. It's like this. We shall see. What are the minimum maximum number of multiple edges? You know, there are, for example, 1,000 realizations. One has no multiple edges at all. One has 100 multiple edges, okay? Multiple edges means 2 vertices are connected by not only one, more than one edge, okay? These are counted multiple edge. And what are the minimum maximum number of chords? Chords we define to remember. And finally, potentially connectedness. This is an old problem in graph theory. There is a theorem by Edmonds about 60 years ago. About 60 years ago, Edmonds gave an algorithm, a theorem, which is slightly difficult, taking time, not difficult, taking time. I shall give you an advantage of omega invariant over an existing theorem. So I shall show you, if you use omega invariant, you can reduce the number of calculations very seriously. So this is an advantage of using omega invariant. Of course, omega invariant is a new invariant, only 3 years old. Not everybody know about it yet, but every day you can apply it to other areas of graph theory, okay? So if you see any resemblance, any similarity between your study areas in computer science, in chemistry, whatever, in applied mathematics, in graph theory, then you can try to apply this omega invariant. Okay, this was the problem. These were the problems we shall be trying to answer in my talk. So let's continue with motivation. Of course, for the motivation, as it's a graph invariant, I should talk about Euler's invariant, Euler's characteristics. If you took topology courses, algebraic topology or classical topology, surfaces, differential geometry, you must know about Euler characteristics or Euler's characteristics. Both are used. You know, in 18th century, one of the greatest few mathematicians, I think the greatest one is Gauss for me. Of course, in ancient times, there are many others in difficult conditions. They did great mathematics. I appreciate them again. But in the modern time, Euler was one of the most clever, genius mathematicians. And he realized that any drawing with a pen or pencil consisting of vertices and lines on a compact orientable surfaces. This is topology, compact orientable surface. I will give you examples of this. We have n minus n plus r is fixed. So what are these? If you are graph theorists, then you know that n usually denotes the number of vertices, m usually denotes the edges, the number of edges, called the order, size, the order, the size, and R is the number of faces. R is the regions, you recall, okay? Vertices, edges, and faces. 0 dimension, 1 dimension, 2 dimension in some sense, okay? So I mentioned about compact orientable surfaces. The classification theorem is very important in topology. Compact orientable surfaces can be classified very easily according to the holes inside them, okay? For example, the sphere has no holes. You cannot go inside it, okay? So it has no hole. So that means the genus, we call it the genus of the surface is 0. So this is genus 0 case. This is torus. In topology, it's a very important, it's connected to elliptic integrals, Fermat's last theorem, many important topics are related to torus. So this is torus with one hole. It's like donuts or Indian breakfast doughs, you know, I don't remember the name. I like them very much. So, and this is two-hole torus. You can have three-hole torus, okay? So up to G is whatever, 1,000 holes you can have, okay? So these are all compact orientable surfaces, okay? So this is the classification theorem. These are first three most easy compact orientable surfaces. Sphere with no holes, torus with one hole, and double torus with two holes, okay? For example, this mag is a torus because you can just go through this, okay? But you cannot go through this because otherwise this part would be empty and you could not put T inside, okay? So this is torus. Topologically, this is a variety of torus, a little bit moved. Because in topology, you can move everything without parting it apart, okay? You can stretch it, anything you can do. Very useful topic, topology. So, two questions now. These are all planar or spherical graphs. You can draw them on the plane or sphere. So what is common in these graphs? N minus M plus R. You remember? N minus M plus R here. Euler's realization. Euler recognized this number is fixed. For example, here, let's take more complicated one. For example, this one. There are 4 vertices, you see, 1, 2, 3, 4. 1, 2, 3, 4 edges, and 1 inside, 1 outside. In topology, we count the region outside as well. But in graph theory, there is only one face. I shall be talking about it in the next slide, in a few slides later, actually. So, this number is, you see, 2, 2, 2, 2, 2, 2, 2. Whatever you do, you draw another edge here, you increase the number of edges by 1, and you must put a vertex. So this increased by 1, this is increased by 1, so they cancel. So this is invariant always, okay? Whatever you do, when you add a new edge, either you increase the number of faces here, or you have to put a new vertex. So either M is cancelled with N or with R, okay? Always you have, whatever you draw, a connected graph, you draw, you get 2 on the sphere, okay? Now we go to square model of torus, okay? Now all surfaces, all compact orientable surfaces are obtained from some paper, stretchy paper, okay? Take a square, identify 2 opposite ends, okay? By folding it, you get a cylinder. Then if you identify this circle here with this circle here, okay? You get at the end torus. So torus is the quotient space of the square, okay? Any square or any quadruple. So these are both torus. How do we know that these are different than the ones before? Because these are, you see, for example, I shall talk on the left one, okay? Or the easy one is right one. You see, these 4 vertices are labeled by 1. So that means they are all the same vertex, okay? Because when you identify this edge with this edge, okay, then you get a, here, you get a line here, okay? So this line and this line will be identified, okay? Like a cylinder. Then this one and this one will be identified. This one and this one will be identified. So there will be a circle here. There will be another circle here. So by identifying these circles, okay, these 4 vertices will be the same vertex on the torus, okay? On the square, they are all different. They look all different places, but on the torus, they will all come to the same point, okay? So the other 4 vertices are inside. So this line and this line, it's like the snake game in your Nokia phones, Nokia mobile phones. There were some game, snake, you remember? Snake was going out of the screen, and from the other side, it was coming in, okay? As much it goes out, as much it would come in, okay? Like Pac-Man. You remember the computer game with Tetris, very old game, like blah, 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 blah. It was eating everything around. So now let's go back to my talk. 5 vertices, you may say 8, but 1, 2, 3, 4 are counted only 1. So 1 plus 4, there are 5 vertices. There are 10 edges. This is a half edge. You see, this is a half edge continuing here. Okay, So this is continuation here. So anything moving here, going through this, comes in here and goes to 4. So 2 is connected to the 4. You see 2, you go here, you come here directly and go 4. It looks like 2 is not connected to the 4, but it is connected to the 4, you see. So if you count all the edges, there are 10 edges and 5 faces. 1, 2, 3, 4, and 5, okay? When you identify both ends, then you will get torus, and there are 5 faces. So here we have 0. Here we have 0 for n minus n plus r. So here we had 2 or sphere with no holes. On a torus with single hole, we have 0. And Euler was a clever man. He realized that this number is fixed and it's equal to actually 2 minus 2g. So n minus n plus r equals to 2 minus 2g. For the sphere, you remember, it was 0, no holes. So n minus n plus r equals to 2 here. You see? On the torus, you have 0. Why? Because genus is 1. Torus has 1 hole. G is 1. If G is 1, then this number is 0. So you see 0. If you get double torus, it will be minus 2. Because double torus will have G is equal to 2. 2 minus 4 will be minus 2. So it will be minus 2, minus 4, minus 6, like this. For all orientable surfaces and orientable graphs, you will get an even number, usually negative, because it starts from 2, 0, minus 2, minus 4, minus 6, like this. Okay, this was the motivation. Now, we draw graphs on some surfaces, not always on the plane, okay? Because sometimes if you draw it on the plane, the lines will intersect. For example, there is the utility problem, very famous problem in graph theory. 3 houses will be connected to electricity center, gas center, and water center, okay? So is this possible without intersecting the lines? Because water and electricity is dangerous. Water and gas, or electricity and gas, intersecting lines can cause problems, okay? Fire or explosion, so it's a problem. So can you draw, can you connect water, electricity, and gas? It's not possible on the plane. So you cannot do this on the plane. The lines will, at least 2 of them will intersect, okay? So you cannot have a planar graph for this problem. So we have higher dimension graphs, okay? Higher dimension surfaces, and graphs will be drawn on this. We use embedding again, like in differential geometry, okay? So whatever is the Euler characteristic of the surface, it will be called the Euler characteristic of the graph. Now, we passed these things. So, final motivation. This was found actually by one of my ex-PhD students. He finished Delan, Sadık Delan, his name was. Still, he has this name actually. He insistingly kept insistingly telling me that this number is important. This number is important. We were working about molecular graphs at that time, but I didn't believe that he could find, a PhD student could find something new, some invariant, graph invariant. I didn't believe him at the beginning, but at the end, after a few months of investigations, indeed, it became out of nothing, but it proved that it is so important. You will see. What was the motivation, actually? The number of leaves. Leaf means degree 1 vertices. You remember I showed you some pictures at the beginning. two graphs, there were one vertex in each graph of degree 1. So this is the number of leaves of a tree. This number is equal to this formula, 2 plus A3. Of course, you've forgotten already A3. What was A3, A4? A3 was the multiplicity of degree 3 vertices, okay? 3 up to A3, 4 up to A4, multiplicities, okay? Remember delta, I'm sure. So A4 is multiplied by 2, A5 is multiplied by 3, A6 is multiplied by 4, A3 is multiplied by 1, A2 is multiplied by, if you put 2, you get 0. So there is no A2 here because the coefficient of it will be 0, okay? And A1 is multiplied by 1 minus 2. This is because of its place. It is on the left-hand side. Normally, it is here as minus A1. So, okay, this is the number of degree 1 vertices in a tree. In a tree, many vertices are there of degree 1. We can organize, rearrange this, the same formula actually, okay? I took A1 to the other side and minus 2, it was 2 here, it was taken to the right-hand side, okay? So this left-hand side, you see this left-hand side is very important. So we call it as omega invariant. You see A3 plus 2A4, 3A5, 4A6, 5A7, it goes like that, okay, up to end. And at the end, minus A1, because if you put 1 here, 1 here, 1 minus 2 is minus 1. So this is the only minus 1, okay? And there is no A2 here, because if you put I equals to 2, this will be 0, as I said in the previous slide, okay? So there is no A2 here in this formula, and A1 is minus coefficient, has minus coefficient. The others are multiplied by convenient numbers. You see 2, you delete 2 from each index, okay? Let's continue. This is a graph. What is its omega invariant? You see? So you have to calculate, you have to determine the degree sequence. There is only one vertex of degree 1. There is only one vertex of degree 2. There is only one vertex of degree 3. 1, 2, 3. There is only one vertex of degree 1, 2, 3, 4 here. There is only one vertex of 1, 2, 3, 4, 5, degree 5. And there is only one vertex of degree 7, which is here. You see, 1, 2, 3, 4, 5, 6, 7. This is a loop, by the way, and it's counted as 2 when counting, when finding the degree, okay? So, remember, we start with A3. A3 is 1. 1 times 1. 1 times 2. 1 times 3. 1 times 5. And going back 1 times 1, but minus, okay? So you get 10. So this graph has omega invariant equals to 10, okay? That's important. But what is the importance of this 10? At the moment, we don't know. Now we shall see some examples, some properties. Of course, in mathematics, when we are suspecting some pattern, some rule, then we look at some classes. For graph theory, these classes are cycles, paths, star graphs, complete graphs, trees, and some others. Some people like wheel graphs, for example. Some people like party graphs. This kind of different graph classes are there. And here, for example, if we looked at these graphs, for example, some cycle graphs, they all have omega equals to 0. And tadpole graph. Tadpole graph are these graphs. A cycle with some tail, okay? So tadpole is little frogs, you know, in the water. They move very quickly like this. So this is like a tadpole. This is the head, this is the tail. This is the head, this is the tail, okay? So what is resemblance between cycle graph and tadpole graph? Cycle graph is a triangle or a square or a pentagon or hexagon, whatever. And tadpole graph is with tail. So tail is not important. That means the number of faces is important. So if you have one face, okay, like a cycle, like a tadpole graph, then you get omega equals to 0. So you wonder that in general, is this true? Or for PN, pet graph, for star graph, for any tree, you get, for example, -2. These are all trees. These are all acyclic, no cycle graphs. They all have -2. So you wonder about the general theorem. For all trees, is it -2, this omega invariant? Yes, it is. So after these observations, we go to investigating properties. For example, the first and very useful property of omega, it's equal to 2 times m minus n. The number of edges minus the number of vertices multiplied by 2. This is the number omega. So that means these are integers. So that means omega is always even integer. Okay, you see direct result. So if omega is odd, because it must be even, there is something wrong. So if omega is odd, then D is not realizable. You cannot get any graph out of it, okay? Because you start the last one, you don't find a place to go, because you need another vertex, but there is no vertex, okay? Because the number is odd. It must be even. So if omega is odd, then the life is over for you. Everything is finished. So you like even case. Another theorem, omega of trees, for example, the title, the necessary and sufficient condition for a simple connected planar graph G to be a tree is omega equals to -2. Okay, so our suspicion was right, okay? For all trees, we suspected that it could be -2. Yes, indeed, it is if and only if theorem, you see, necessary and sufficient condition. So they are all having -2 as omega invariant. The proof is very easy. Omega was equal to 2 times m minus n, we just see. It is equal to -2. That means n minus m is equal to 1, okay? So Euler characteristic was n minus m plus r. N minus m is 1 plus r equals to 1. That means, so r is 0. R was the number of faces. So there is no face. There is no face means it's a connected graph, you see. So it's a tree. So for all trees, we have omega equals to -2. Another important result, omega is additive. So if you have some components, it's not a connected graph. You have some components. You calculate omega of each one, then it's additive. You can find the total omega invariant by adding them. This is maybe very most important and very beautiful result. The number of faces of a connected graph. I will not go through all. The number of faces is omega divided by 2 plus 1. So you are given such a set, my friends. Listen this part. You are given such a set, 1, 1, 1, 2, 2, 3, 3, 3, 4, 4, 5, 5, 5, 6, 6, whatever. Total must be even. Then you calculate, you don't know realizations. There are lots of realizations, probably millions, billions, okay? So you don't know how many faces there will be. Because if you know the number of faces, it will be very easy for you. You will not go further, okay? You will know where to stop at least. So R is equal to omega divided by 2, half omega, let's say, plus 1. This is for connected. If it is not connected, then there are C components. Then here there was one, you remember, in connected case, because connected means one component. If there are more than one component for a disconnected graph, then the number of faces will be this number, okay? Increasing. If you increase the number of components, the number of faces will be also increased by this. This is another result we shall be using. The number of components is has a lower bound, okay? It is bounded below by minus omega over 2, which is n minus m, if you remember, okay? I shall use them, so I will recall these results. This is very useful. If you have a tree at some part of the graph, at some end, then you can cut this tree. In real life, don't cut any tree, but here we cut the tree because we don't want lots of calculations. So it says if you have g plus t, t is a tree, equals to omega of g. So if you cut some tree parts like this, for example, here from this vertex on, this is a tree, okay? You delete this, you delete this, you delete these two edges, and you delete these three edges, okay? Then you get this square with one, line connecting two opposite vertices, okay? So the omega invariant of this is equal to the omega invariant of this. So why try to calculate this much horrible thing? Again, you can calculate. This is the vertex set of the degree sequence of this graph. And this is much easier, of course. 4 vertices, 2 of them are of degree 2, 2 of them are of degree 3. So both have omega invariant equals to 2. So we can always cut 3 parts in a graph to calculate omega. This is the relation between omega invariant and Euler characteristics. I skip. And now we move to main parts in the last maybe 15 minutes. I don't know, about 15 minutes I calculate. We defined some special connected realizations of any realizable degree sequence, okay? We called this fundamental realizations, and there are 3 classes. This is most important slide. There are 3 classes. You classify omega if omega is non-negative, 0 or positive, if omega is -2, and if omega is less than or equal to -4. So these 3 groups are important, okay? Omega is non-negative, let's say positive or 0. Omega is -2, and omega is less than or equal to -4. What about -1, -3? It cannot be odd. Remember, it must be even, so there is nothing missing. So in the first case, omega is non-negative. We have such a theorem. It says that if omega is non-negative, D is potentially connected. That means there are some connected and there are some disconnected realizations. And if you want connected realizations, okay, if you want connected realizations, it has some cycle of this number we shall use, some loops, some chords, and A1 pendant edges. This is the structure of the graph. Of course, you can order these things, some loops, some chords, we know the numbers, whichever we like. For example, someone could say, could ask for maximum number of chords or maximum number of loops, okay? Then it's an extremal problem. You can solve it. I shall give examples. So that means if omega is non-negative, at least 0, then all realizations must be cyclic. This is one theorem we shall be using. This is another theorem. If omega is 0, a special case, you see, a special case of the previous theorem, it was omega is non-negative. Now only omega is 0. In this case, it is realizable as a connected graph. Then if it is its cyclic fundamental form cannot have any loops, multiplets, and chords. That means it has one cycle only. Just one cycle means unicyclic. The length of this unique cycle could be any number. You see, I shall give an example. This length of unique cycle could be between 1 and this sum, A2, A3, A delta. We used this sum before, you remember? It's an important sum, I said. So, examples now. Now you can rest a little bit. Consider the degree sequence. Omega equals to 0. You can calculate omega first. I calculated it for you. Omega equals to 0 implies that any connected realization will be unicyclic. You remember the last theorem. So this is unicyclic with octagon, 8 vertices. You see? This is another one with 7 vertices. How we obtain it? V1 is moved to here, okay? This is a vertex of degree 2. This is another vertex of degree 2. So the degree set is the same, you see? So if you move all these vertices, V2 is moved to here, then you see V1, V2. Then you move V3 to here, V4 to here. Then at the end, you get a triangle instead of octagon or heptagon, I think. So all are realizations of this degree sequence. As omega is 0 and these are connected, then they are all unicyclic. There is only one cycle, but the cycle length is between 8, 7, up to 3. You will see at some point more pictures about this, okay? Just continue now. The second case, if you remember, omega is -2. You remember at the beginning, I gave you that a result. I proved a result. Omega is equal to -2 if and only if it's a 3. Remember, for 3's. So the realization theorem says that if omega is equal to -2, there is a caterpillar tree. What is a caterpillar tree? It's something like this, okay? Then as I have little time to continue to finish, I will not go to details, but this is a caterpillar tree. The head and the legs of the caterpillar, you know, normally we assume it has 40 legs, you know. So this is how we obtain the realization in this case. And the final case, you remember, omega is less than or equal to -2. This is the mixed case. You again start with this number length cycle, and you add some loops, pendant edges, as in the first case, and we get some K2s. K2 means complete graph with 2 vertices and 1 edge, just line like a pencil, okay? So this is mixed case. I will not go into details, but the mixed case, you see K2s. There are some K2s, and this is the cycle. Omega is equal to -8. So this is mixed case. It is less than or equal to -4. Now let's go back to the problem. I shall be finishing with the solutions of the problems actually I gave you. What was the first problem? Is the degree sequence realizable? And what is the cyclomatic number? Now, the degree sequence, if you calculate omega of it, it's 12. 12 means it is even. So this degree sequence is realizable. That means there is at least one graph having these vertex degrees, okay? Cyclomatic number, you remember I talked about very important theorem. It was omega divided by 2 plus 1 for connected. This is connected, of course, graphs. So the cyclomatic number is omega divided by 2 plus 1, which is 7. So there will be always, whatever connected graph you draw, there will be 7 cycles. Okay? In different places, doesn't matter. Total 7. If you have 6 cycles, it's not a realization of this degree sequence. Second problem was find 2 realizations with minimum and maximum number of components for this degree sequence. You remember this degree sequence I mentioned? Yeah. By corollary 10, of course, you may not remember the numbers, but a lower bound for the number of components were given by this number. You remember n minus m it was also. So if you calculate omega, if you remember omega, I don't remember what it was. I think it is minus 12. 12, yeah, omega is 12. So 12 divided by 2 is 6 minus 6. C is number of components. Is it useful information to know that the number of components or the number of something is bigger than minus 6, larger than minus 6 or equal to? It's a positive number, so it's no use. So C can be taken as 1. So we have at least 1 component because C can be 1. C is the number of components. 1 component is possible. Maybe there will be some disconnected ones as well because C is at the moment we know that C is greater or equal to minus 6, which is no information at all. By theorem 13, we can have some connected realizations. You see here the number of loops, the number of multiple edges, and the number of chords are shown. This is, for example, 1 loop, no multiple edges. Multiple edges means, for example, here we have 1 normal edge, 2 multiple edges. Okay. For example, here multiple edges are 1, 2, 3, 4, 5. You see 5 multiple edges. There is no chord here. Here, for example, there are some chords. 1, 2, 3, 4, 5 chords. You see here there are 2 chords. Here there is 1 chord and the other one is multiple edge. Here also a multiple edge. Here also a multiple edge. For example, this is the answer of maximum number of chords realization. This is the answer of maximum number of multiple edges realization. Okay, these are all answers to several questions. Of course, you can change the order of the vertices and you can have similar realizations as well. We still don't know the total number of realizations. Remember? No. Now we go to maximum number of components. This is also a nice theorem we gave. You remember there are some odd degrees, 1, 3, 5, 7, like this. You calculate, you add up the multiplicity of these vertices, A1, A3, A5, and you divide them by 2. But you do the same for the even degrees, 2, 4, 6, whatsoever, okay? And you calculate the sum of all the multiplicities without dividing by 2, okay? Even degree multiplicities are added all together. The odd ones are added all together, but divided by 2. This is because of handshaking lemma, actually. So this is what we get. And this is the maximum components you can have. You cannot draw this degree sequence as having 6 components, for example, okay? This is maximum 5. So this degree sequence can be drawn by 1 component as a connected graph, 2 components, 3 components, 4 components, and maximum 5 components. You cannot draw it by 6 components, okay? This was another question. Find the number of distinct cycles. Distinct cycles is really difficult, but remember the formula, beautiful formula for distinct cycles, omega divided by 2 plus 1, as this is connected. So the degree sequence of this is this one. Omega is 14. So 14 divided by 2 plus 1 is equal to 8. So there are 8 cycles. You can count 1, 2, 3. It's difficult to count. So it's better to apply omega invariant. This is about the chords, the number of chords. This graph is similar with this graph. They are isomorphic. You can check it. For example, F is connected to B, E, and G. F is connected to B, E, and G. You see, you can check all vertices, the same vertices, the same connections, okay? So here you can count the number of chords, 1, 2, 3, and 4 around this quadrilateral. So there are 7 chords, okay? So sometimes you can do this, but would you see that this graph can be drawn as this graph easily? No, you couldn't see that, okay? There are some examples like this, handy examples we use. So it's not always possible to see such easily isomorphism. So theorem 18 below helps us to find this number. Omega divided by 2 is equal to the number of loops plus the number of multiple edges plus the number of chords. Okay, so this is very, very strong actually result in case of omega is non-negative. Okay, because loops, chords, and multiple edges, they add up to omega divided by 2. As you know, omega, the left hand side is fixed, so loops, chords, and multiple edges will be equal to, the sum of them will be equal to this number. Okay, so this is nice, very combinatorial problem. So for example, in our case, omega was on 14. 14 divided by 2, 7 is equal to the sum. You see, in all results, in all realizations, you will have this number giving you 7 in total. Okay. In our case, there are no loops here, no multiple edges here, so no loops, no multiple edges. So that means the number of chords will be 7. Okay, the number of chords will be 7. But instead of counting this, you can calculate this formula, this theorem. This is a generalization with C components. You get here some number C minus 1. Another problem, how can we find its connected realizations? I don't have time. I have to finish probably in 1 or 2 minutes. Here I shall give you this problem first and last. How can we decide whether a realization of a given degree sequence is connected? This is an important problem. Connectedness. In mathematics, connectedness, compactness, these are very important topics. For example, this degree set, this degree sequence has 2 realizations. You see, has 2 realizations. Okay, so one is connected and the other has 2 components. You see one small piece here and another one here. Okay, so this given degree sequence can be drawn as a connected or disconnected graph. There are many other ways, of course. What can we guarantee? We know that this is most strong problem, most strong result we gave. Omega is less than or equal to -4 means all graphs will be disconnected. Surely, if omega is less than or equal to -4, all graphs are disconnected. But if omega is greater than or equal to -2, then the graph is potentially connected. That means at least one realization is connected, probably more. But there are also disconnected ones. There is a potential to have connected ones, okay? So that means omega is less than or equal to -4. D cannot be forcibly or potentially connected. If omega is less than or equal to -4, surely you have disconnected graphs, like here in this case. Omega equals to -4 means there are 3 or 2 components. You cannot have a connected graph. At least 2 components or 3 components? What was the maximum number of components? You remember, you can calculate. So, okay, I shall, I think, stop here. Thank you for all listening me. Okay, thank you. I hope it was useful.
Thank you, sir. Thank you, sir. Thank you so much for your presentation.
Thank you.
Thank you for enlightening the session. It's the time to ask the queries, and I ask the participant to post the questions in chat box or unmute yourself and then ask your queries.
Hello. Sir, there is a question from Sarati Jayanti. Is there any scope for topological graph theory?
Yes. Topological graph theory is very important nowadays. Most of the papers are written in topological graph theory because, as I said, Harold Wiener in 1947, he defined some mathematical formula for the boiling points of isomers of some alkane classes. So it has applications in chemistry. But nowadays, there's this problem, I should say. Nearly every day in ResearchGate, I get about 10, 15 papers in my area. And most of them are topological ones, topological graph indices. And they say that these papers, these calculations are important because it has applications in chemistry, but they don't say the applications. This is the problem with many papers. This is why they don't get accepted in good journals. If you find some application in chemistry or in sociology or in medicine, it has lots of applications because they can be published in very good journals. So topology is very much into this area, graph theory. Okay.
Yes, sir. Thank you, sir. And one more question from Sashikala S. She wants to know about the mathematical tool that was used for draw all these graphs which are used in your presentation.
Yeah. In general, there are some programs to draw graphs, but in my talk, I didn't need that much computer programming, so the pictures were ready already in my files. So I usually draw them in Word and transfer them to JPEG. But young people, I'm sure they are better experienced with mathematical programs, and they might try lots of programs, even Maple, you can draw in the latest versions. In Magma, in Maple, there are, I don't remember, I don't use them very much because I don't do lots of calculations, this kind of things. Mostly I study topological things, so I don't need computation too much, enumeration. But if you study enumerative things, then you should use some tools, as Shashikala asked. There are indeed very nice tools, and if you Google them, you can find all the programs. But some of them, maybe you may be expert a little bit in programming, because there are codes usually. You have to download some programs, some codes. I'm not so good, so I try to draw them by hand. If they are too complicated, I ask to my students.
Okay, sir. And one more question from Madhvesha Maudgalya. Can we take coronavirus structure and find out the topological properties and study its structure?
Yes, you can actually, since coronavirus has been around for more than 1 year, 1.5 years. I read maybe about 50 papers about corona virus. And some people try to, not the coronavirus itself as a model, but the chemical medicines. They have, chemical structure as molecules, and people study some topological indices of these medicines, okay? It is consisting of carbons, hydrogens, oxygens, nitrogen, whatever. It has a structure. You get a model of this structure as a graph. You study distances or neighborhood vertices, neighborhood matrices, some matrices. You study, okay? This could be matrices, this could be functions, this could be adjacency, this could be distances. There are many ways of studying graphs. So if you study a graph, then you study the chemical compounds corresponding to it. So it is very useful, but I don't see any practical application about solving this virus problem. They all calculated some things. Some of them draw some diagrams as well, but no cure yet mathematically, unfortunately. It would be beautiful if some mathematician could find some cure to this omega coronavirus. But one more thing, corona is a kind of product in graphs, okay? Corona product of graphs. This is something mathematical, no relation with this coronavirus. Okay.
Yes, sir. One more question from Sundareshwaran R. Can we construct a connected graph with sigma of G is less than or equal to K?
What is sigma G? Omega, you mean?
Yes, I think it's for
Sundareshwaran.
omega. Yes.
Probably omega, it should be, I read it now. Yeah, of course, omega is, for even one value of omega invariant, you can have millions of them. So it is possible, but this is a very big question because it's, for example, let's say K is 4. Then we are looking for all graphs with omega value equals to or smaller than 4. That means we are looking for omega invariant equals to 4, 2, 0, -2. It's an even number, you remember? -4, -6, -8, lots of graphs. So it's a very big problem. You have to restrict yourself. For some values of K, then you can try to construct graphs. But if omega is, of course, one more sentence I have to tell. If omega is less than or equal to -4, then no connected graph. You remember? I gave the theorem. Okay.
Yes, sir. Thank you, sir. So I think there is no queries further because of your crystal clear explanation, sir. Thank you, sir. Now I would like to end up today's session formally with the vote of thanks.
Now I call upon Mrs. S. Rajeshwari, Assistant Professor, Department of Mathematics, to deliver the vote of thanks.
Thank you, ma'am. A very good evening to everybody present here. It's my great privilege to present vote of thanks. I take this wonderful opportunity to thank our eminent speaker, Dr. Ismail Naci CANGUL, for sharing his immense knowledge in graphs and its application. Today's session gave deep insights into the topic and provide a chance to learn such facts and graphs. Thank you, sir. I would like to give a special thanks to Dr. R. Kavita, Vice Chancellor, DMI, St.Joseph University, Zambia, for spending her valuable time for the FDP. Also, I would like to thank our college principal, Dr. R. Rupan, who is the pillar of this FDP. I thank Reverend Sister A. Malarjodi for her support. Also, I would like to thank the faculties of Mathematics Department for their timeless effort for this FDP. And I would like to thank to faculties from various colleges across the countries who are giving their support by rendering their active participation. And in last, I would like to thank the Visual Communication Department and the System Admin for their technical support. Once again, I thank you all. Thank you very much.
Thank you, ma'am. Now it's time for photo session. So I kindly request the participants to switch on your camera.
Professor? Professor? Professor, thank you very
Kindly
much.
switch on your camera.
Bye, bye,
Kindly-
Professor. Nice meeting you. Bye, Professor. Thank you very much. Thank you.
Kindly switch on your video for photo
Thank you,
session.
sir. Thank you very much. Thank you.
Kindly switch on your video for photo session.
Excuse me, do you have any attendance or feedback form?
Yes, sir.
You will send her.
Sir, it is posted in chat box, sir.
Okay, I will see.
You can find the link in chat box.
I didn't get that.